Okay, so I'm going to go over the homework for Module 15. You were supposed to read pages 367 to 383, stopping at lenses, your student notebook, and some questions in the study guide. So I'm going to go over those with you. We're going to start in your student notebook. You are going to fill out page 188. It's for the different theories of light. So the first one is the particle theory. That was from Isaac Newton. And it says that light comes in little individual light particle packages, which we also call photons. We learned that in some previous chapters. Um, then you've got the wave theory. That was from physicist Christian Huygens. And he says that light is a wave, not a particle. But through the years, scientists have decided that light has qualities of both of those theories. So they came up with another theory called the quantum mechanical theory of light. And that's what they kind of still go with today. So that says that light can act as either a stream of photons, which are those tiny little packets of particles, or as a bunch of electromagnetic waves, which are waves composed of electrical and magnetic energy that oscillates, which moves back and forth. You'll see that word a lot this chapter. Oscillate just means it moves back and forth. So that's page 188 in your student notebook. You're going to fill out those theories. Let's go to number 3 in your study guide. We'll start with those questions. So number 3 in your study guide says that sound waves cause air to oscillate, move back and forth. What do light waves oscillate? Well, light waves oscillate a magnetic field, which is perpendicular, forming a right angle, to an electrical field. And that's what the quantum mechanical theory of light kind of says. That light waves move back and forth in perpendicular a magnetic field to an electrical field. Light waves are also called electromagnetic waves. So when you hear electromagnetic waves, it's also talking about light. Number 4. What does Einstein's special theory of relativity say about the speed of light? Well, it says that nothing can travel faster than the speed of light in any given substance. Speed of light it just travels the fastest. Nothing can travel faster than that in any given substance. So if you have a sound wave and a light wave going through water, light travels faster. If you have sound wave and a light wave traveling through air, light travels faster. It's just saying if it's in a race with something else in any substance, light is going to travel the fastest. Number 5. Light is traveling through water and suddenly breaks the surface and travels through air. So did the light speed increase, decrease, or stay the same once it left the water? So what it's saying is light is traveling through some water and suddenly it breaks the surface of the water and travels into the air. So does the light speed increase, decrease, or stay the same? What happens here? So the speed of light travels fastest in gases, which is your air. That's the fastest it's going to travel. It travels the fastest in air or gases. The speed of light travels a little slower in liquids and the slowest in solids. So if it's traveling through the water and breaks into the air, then the light speed is going to increase once it hits the air because it travels fastest in gases. So the light speed increases. Okay, let's see here. I think number 6. Yeah, number 6. So order the following colors in terms of increasing wavelength: orange, violet, yellow, and green. So we're going to order them from the smallest wavelength to the longest wavelength. So there's a chart in your book on page 371. It's figure 15.2, and it shows you how long each of the wavelengths are for each different color. So all the colors, blue, indigo, red, orange, yellow, they all have different wavelengths. And it shows you on this chart which are the longest and which are the shortest. So if we're going to order those colors from shortest wavelength to longest wavelength, that would go from violet, green, yellow, and then orange having the longest wavelength. So violet has the shortest, and then green, and then yellow, and then orange has the longest wavelength. Now, number 7 says to order those same colors in terms of increasing frequency. So we're going to go from the lowest frequency to the highest frequency. So on this, you would go from the lowest frequency would be orange because it has the longest wavelength, and then it would be yellow and then green, and then violet would have the highest frequency, and it would also have the shortest wavelength. So if it has a small or short wavelength, it's going to have the highest frequency. If it has long wavelengths, it's going to have slow, low frequency. So number 6 would be violet, green, yellow, orange. Number 7 would be orange, yellow, green, violet. Okay, number 8. Do radio waves have higher or lower frequencies than visible light? And what about X-rays? So there's also a chart on page 372 in your book. It's also a chart that you're going to fill out page 189 in your student notebook. So if you want to look at that and check it on your in your student notebook, page 189, you're to label the chart. So the first blank there under the scan looking deal, radiation symbol, is gamma rays. And then you've got X-rays. UV rays are next. That's what SPF 30 is for. Remember, we learned about how our ozone layer protects us from a lot of those ultraviolet rays. But that's what the sunblock is for, so that we don't get burnt up by those UV rays that are still coming through. And then you've got visible light, and then infrared light, microwaves, television waves, and then radio waves. That should be what your chart kind of says. Now, that goes from gamma rays having the shortest wavelengths to radio waves having the longest wavelengths. So gamma rays with the shortest wavelengths have the highest frequencies. Radio waves that have the longest wavelengths have the lower frequencies. So the question is, do radio waves have higher or lower frequencies than visible light? So if you look at your chart, you'll see radio waves are on the far end of long wavelengths, and visible light is a little, above half. So for radio waves, we'll have lower frequencies than visible light because they're on that far end. Now, X-rays, they come before that visible rays. They're a little further up on the chart. So X-rays have higher frequencies than visible light. Okay, let's see. We skip on down to number 11. So in that diagram, will the man see his foot despite the fact that the mirror does not reach the ground? So if you read the chapter, yes, you'll know that he'll see his foot, because this is reflection, and this is how reflection works. So light travels from the foot, reflects off of the mirror, then hits his eyes. Then his brain has to form that image. It says to form that image, and forms that image into the mirror. It's really weird to understand. So that's, yes, he will see it because the light will hit his foot, and at that angle that it hits his foot, gets to the mirror, it will go straight to his eyes because that angle is just right. It forms that right angle. So you'll have, it's perpendicular to each other. Okay, number 12. When light travels from one substance to another, what two things can happen to the direction of the light rays travel? So when light travels from one substance to another, let's say it's going from air to water, water to solid, different things, or solid to water, or whatever the case may be. So first, light can be reflected. And that's where the light rays just bounce off the object onto something else, and that's what we just talked about just now. Or it can be refracted. So to explain that, when light waves are refracted, They begin to travel through the object, but they usually bend their direction of travel because of their change of speed. And why is there a change of speed? Because remember, sound waves and even light waves travel at different speeds depending on if they're going through a liquid, a solid, or a gas. So if it's traveling from one speed to another, that difference of speed, would I say that right? If it travels from one substance to another, it changes speed, and therefore it's going to change direction of it bends. The light bends. When it changes the speed, it changes the direction. We call it bending, but that's kind of what it means. Okay, number 14. When you look at objects underwater from above the water, they appear to be at different position than their actual position. Why is this? This is hard to explain, so I'll try. So to see objects underwater, light has to travel from the object to your eyes. So the light has to travel out of the water and into the air, causing it to bend, causing the speed of light to change, which causes it to bend towards your eyes. So this causes you to see a false image of the object in a slightly different location because of how the light rays are refracted coming out of the water and into the air and into your eyes. To further understand this, there's an example in the book. It's on page 381. It's figure 15.7. If you'll look at that and kind of study that for a second, that will help you explain number 14. And the last one, number 15. In order for you to see a rainbow, what 3 conditions must be met? So the next time you see a rainbow, I'm sure this is what you're going to be thinking about, right? The 3 conditions that must be met in order to see a rainbow is number 1, the first condition, is there must be water droplets in the air. And that's why you see rainbows during or after rain, because the air is full of water droplets still. It's raining today, but right now there's no sun, which is number 2. The second condition is the sun must be shining on the water droplets from behind you. So yes, in order for you to see a rainbow, the sun should be behind you. I hope this comes to mind next time I see a rainbow, so that I can test this theory out. It's not a theory, I guess, but I want to see if it's true. And then the third condition, in order to see a rainbow, is the sun has to be at a certain height. So in other words, the light rays from the sun have to hit the droplets at just the right angle, at a certain angle, in order for them to refract coming into the droplet, and then reflect, and then refract again coming out of the same side of that water droplet. So if you've got a water droplet, you want the light to come in this side, refract. It's going to hit this side and reflect and come back out and refract the same side as this water droplet came into. So that all 3 conditions have to be met, and that's why you don't always see a rainbow when it rains, because if those 3 conditions aren't met, then there won't be a rainbow. That's all the homework. So your homework for this week is to finish the chapter. I believe that is pages 383 to 392. Do experiment 15.5 that will show you a little bit more about light. It's not hard. Go ahead and do that. If you can, send me a picture. That'd be cool. And then do your study guide questions 16 through 20. And study for the test. And we'll do it like we did the last time. I'll send you the answers to your homework and let you review those. And then I'll send you the test for that chapter. And that is it. We're going to be done for the year. So really, next Monday, or Tuesday, I guess, will be our last day of school. But I'll get to see you guys next year in another science class. Hopefully I can figure it out with you too. Until then, I'll see you later. Bye.